All right, welcome to our first video in our series on the Enigma project. The Enigma project is named after a device created by German cryptographers in World War II that was this funny looking box you see on here on the right. Looks like an old-fashioned typewriter. It was used to be able to send and receive encrypted messages, and even though the Allies could intercept those messages, even if the Allies had an Enigma machine of their own, because there were so many possible configurations of the machine, it was impossible to know what the message was. And so, legendary computer scientist, some consider him the father of the modern computer, British mathematician Alan Turing, worked during the war at Bletchley Park and helped to create a computer that would crack the Enigma code so that they could determine what the daily settings were so that they could decrypt all the secret messages. This story is told in the movie The Imitation Game. It's deeply moving. I highly recommend you check it out. But the purpose of this little project is we're going to do a little unit on encryption. There's just going to be 5 checkpoints, a few basic ciphers, and then the much more complicated, much more interesting final Enigma checkpoint, where we're going to create a digital equivalent of the machine itself, which I think is pretty cool. Before we get into the basic version, what did the Enigma machine look like? Well, there's this awesome website that does a simulation of the Enigma machine. And what you can do is you can determine what rotors you want to use. They had 5 of these different cylindrical rotors that would slot into the machine. You could set up what are called different plug board settings, mean that maybe I set all of my E's are connected to M's, which means all my M's are connected to E's. And you could actually translate a letter through this machine, and you could watch it move. The electrical current moves through the plug board, through the rotors, off something called the reflector, back through the rotors, back through the plug board, and you could see how one letter becomes another. What makes this so brilliant is I could do the same letter again, but because one of the rotors is spinning as I'm entering letters, that means I'm going to get a different letter that comes out. So A the first time became D, A the second time became T. It's obviously a very, very challenging device to make, but we're going to break it down into manageable parts, and by the time you're done, you will have made your own digital equivalent of Enigma. So where do we start in this project? Well, the first thing we're going to do is just something called a basic Caesar cipher. A Caesar cipher is where you take each letter in the message and you shift it by an amount. We're going to consider the basic Caesar cipher to be a shift of 1. And what does that shift mean? It means you either move up the alphabet or down the alphabet. If I'm encrypting, then I will take every letter in my message and I will move it up the alphabet by 1. If I was encrypting hello world, well, the next letter that comes after H in the alphabet is going to be I. The next letter that comes after E is going to be F. The next letter that comes after L is going to be M. If I'm going backwards, if I'm decrypting, that means I have to drop all the letters down by 1. So if I decrypt an I, it goes back to H. If I decrypt an F, it goes back to E, and so on and so forth. What does this look like when we're running it? Well, I can show you. I have my Enigma code in this tab right here. I won't show you that, obviously, because that would defeat the whole purpose. But if I go ahead and run this thing, and I say we're going to use forward arrow to mean encrypt, move into the encryption, and we're going to use the backwards arrow to mean decrypt, moving out of the encryption. I'm going to say, let's go ahead and encrypt into a Caesar cipher. And we're going to go ahead and say, how about mango, something like that. And that became NBOHP. And that makes sense. After M becomes N, after A becomes B, so on and so forth. If I go to decrypt that same thing, decrypt NBOP, it should give me mango back. So that's what it should look like. I think, do I have it set up? Yay! I have it set up so the quit's going to be used. So what are the requirements for this checkpoint? What do you need to get done? Thankfully, it's not too difficult. We want to have, what are the requirements? Number 1, create yourself a user input loop. You know, we've created user input loops for FRAC calc. We've done it for VisiCalc. We've done it for a whole bunch of different projects in this class. So you're going to use a while loop and a Boolean. If they say quit, you turn that Boolean to false, your while loop shuts off. Hopefully a user input loop is something you're comfortable with at this point. The next thing is we need to create a process command method whose job it is to handle these commands, right? So if your user didn't give quit, if they're not trying to shut off the loop, then go ahead and take the string of their input as taken in by a scanner and ship it off to a method called process command whose job it is to interpret what's the kind of command you need and what's the kind of encryption you need. Are we encrypting or decrypting? And what's the message you want to translate one way or the other? So what that means is in process command, we should consider that the first token will always reveal, the first token determines type of encryption or decryption. When we encrypt, we're going into the gobbledygook, the gibberish message. When we decrypt, we come out of that into something that should make sense, decryption. Was that not decryption? I thought decrypt. Well, that could be embarrassing. I really thought that's how you spelled that word. Maybe that's just the text editor for Eclipse betraying me. That's all right. So the first token will always determine the type of encryption. So what that means is over C is a basic Caesar cipher. Over C with a number is an advanced Caesar cipher. This is where we can move either up or down the alphabet now by more than one. So it could be 3, up by 3, or decrypt Caesar 7 means we're going to go down the alphabet by 7. The other one is an affine cipher, which we'll cover in a later video, and a rotor cipher. And then we'll get into Enigma is really its own special creature. We'll cover Enigma in its own video as well. But you can always count on that first token to be what tells you what kind of encryption. The other thing I would say is let's have everything will be uppercase. And let's go ahead and ignore spaces. So if I try to do encrypt hello there, it will preserve the space. The space doesn't do anything fancy. All right. So those are the requirements. You have to be able to handle encryption and decryption. Go either up by 1 or down by 1. What recommendations do I have? Well, the first thing I would tell you is to remember Unicode. And what's Unicode again? Unicode tells us that every character, whether it's a letter or a number, punctuation, any symbol that we can generate, has a numerical equivalent. What does that mean? That means that if I were to cast to an int the char capital A, so capital A is a letter, right? It's a char. If I cast that to an int, this will convert it to 65. Capital A is 65. If I do this to a B, think in your head for a second, what's that supposed to be? It's going to be 66. That's right. So what that means is we can convert letters to numbers, and we can also convert those numbers back to letters. For example, if I said char of, how about 67, then we're going to, how about I spell the word convert correctly? Then that's going to change things back to a capital C. So what's the pseudo code here? Well, I'm going to go ahead and skip user input loop. I assume that you can do that okay. I'm going to go ahead and skip, we're going to set up a for loop to visit every letter to convert it. And that's actually where we're going to start. So let's say, your user said encrypt with a basic Caesar cipher the phrase hello there. I would send message to the process command method. Once we're down there, I would use a for loop to traverse the entire string message, right? So hello there is what would get shipped down there. I want to visit every letter. We're going to visit the H, then the E, blah, blah, blah. Then I would probably, I guess actually I should have, let's make this step 3. Before we do that, I'm going to recommend you prime the loop with an empty string variable, right? So let's send something like, string returned string equals empty, like that. And so what you can do is when you go through the message, whenever you successfully translate one of the letters, add it to return string. So we're going to convert H into an I. Once we've got that I, add it to return string. And then the loop will move on to the next letter. You've got this E, let's convert it to an F, add that to return string. Now it's I and F. All right, so we use a for loop to traverse the entire string message. Then I would grab each individual letter with char at, and I would convert to an int using explicit casting. And maybe I'll make this its own step so we can break this down. Convert to an int with explicit cast. Can you do it implicitly? You can. It's certainly possible to do something like this. You can say capital A plus 0. That also converts to 65, but ask yourself the question, why is that worse? If it does the same thing, if you're using fewer characters, why is that worse? And the answer I would give is you're not being clear about the intent of your project there. So convert to an int with an explicit cast, increase or decrease that int by 1, depending if you're encrypting or decrypting. Convert int back to a char, and then we go ahead and add the converted char to returned string. And then eventually you should be able to print that out. Okay, so that's everything you need to know for part 1 of the Enigma project. Thanks for watching.